Welcome to part 2 of the tutorial. In this part, we're going to see how can we identify clusters using algorithms for accurate network clustering. So let's get started. So as I mentioned in the first part, there are over 1,000 algorithms proposed in the last 50 years for network clustering. These algorithms come from different fields, they are applied to different applications, and they solve different problems, variations. This is the input to the network clustering problem. However, as I also mentioned, a few fundamental ideas reappear in many algorithms over time. These algorithms can roughly be divided into four categories. Cut-based algorithms, which try to minimize the cut size or the cut ratio. Modularity-based algorithms that maximize the modularity of a partition. Inference-based algorithms that maximize the likelihood function over the partitions under some statistical formulation for the problem. And learning-based algorithms, where you train a classifier model to predict the cluster of nodes. And the main idea of each of these categories will be presented in this part, along with an example, a small example. So let's get started and look at the very beginning, which is the minimum cut problem. So the minimum cut is to find the partition that minimizes the cut. And in this example, we have a small network, and the minimum cut of this network is 2. And you can achieve this clustering by, for example, isolating node 4. This problem is related to the maximum flow problem. The maximum flow and the min cut are equivalent problems when you have a fixed source and destination of nodes in the network, and they are efficient algorithms and linear programming formulation since the 1950s to tackle this problem. The most famous one is the Ford-Fulkerson algorithm for maximum flow min cut. And one good news is that min cut is polynomial. This is known since the 50s, but it's also polynomial near linear time. So a randomized algorithm that provides the minimum cut in time O(n squared log n) was proposed in 1996, and the first deterministic near linear time algorithm was proposed only in 2024, this year. And the paper that proposed this algorithm was published in SODA, an important conference in algorithms, and it received the Best Paper Award. So here's an example of a very classic problem still being tackled by theoretical computer scientists. Good. And this leads us to the graph bisection problem, also known as the planted partition problem. And here we have partitions of equal sizes. So let's consider the case of two clusters, and I'm still trying to find the minimum cut, but now the cluster sizes have identical sizes. And in this scenario, finding the optimal partition is NP-hard, as opposed to the minimum cut that we just saw. So several heuristics and approximation algorithms were given to this problem, and a cornerstone is an algorithm proposed by Kernighan and Lin in the 1970s. So here how the algorithm works. You start with a random bisection of the graph, C1 and C2. For example, you place all even nodes in one cluster and all odd nodes in another cluster. Then you consider all pairs of nodes, one node in U, one node U in C1 and a node V in C2, and you consider the reduction in the cut size when you swap their clusters. So you do that for all pairs. Each pair gives you a reduction or an increase in cut size, and then you select the pair that reduces the cut the most, and you swap their clusters. So the greedy step is just selecting the pair that reduces the most. And then you return to step 2 by considering all pairs again and choosing the pair that reduces the cut size the most. And the algorithm stops when you cannot find a swap that reduces the cut size. So each greedy iteration considers all pairs, that's in the order of n squared. Computing the change in the cut size when swapping a pair is proportional to the node's degrees, so it's not so expensive. And the number of iterations of these algorithms depends on the initial bisection and other factors. And this is just an approximation, it's just an heuristics. The algorithm does not always return the optimal solution, given that this problem is NP hard. So let's take a look at an example. Here's our little graph with 6 nodes. We place all even nodes in cluster 2 and all odd nodes in cluster 1. And the cut size here is 5. There's 5 edges crossing from one cluster to the other. If we consider all pairs of nodes in cluster 1 and cluster 2 and the reduction in the cut size when you swap them, you'll find that the pair 1, 6 reduces the cut the most. So we swap 1 and 6 from clusters, and that will give rise to cluster 1 being 1, 4, 5 and cluster 2 being 2, 3, 6. And the cost of this new allocation is 2. And if you iterate again, you would find that there's no swap that can reduce the cut size further. So we stop here with this allocation, which is actually the optimal allocation. So that's the Kernighan and Lin algorithm. So now let's talk about a very different approach to minimize the cut size and even the cut ratio that is based on the spectral decomposition of the graph. So we start by considering the graph Laplacian matrix, which is a matrix that is determined by the diagonal of the degrees, matrix D, minus A, the adjacency matrix. So that's called the Laplacian of the graph. And now what we're going to do is we're going to consider the spectral decomposition of this matrix. And we're going to find the eigenvalues to be lambda 1, lambda 2, all the way up to lambda n, and the corresponding eigenvectors will be v1, v2, v3, all the way up to vn. Okay? So now we have this decomposition of the Laplacian, and the key idea here is that these eigenvalues and eigenvectors of the Laplacian reflect something about the structure of the graph. So spectral graph theory is the area of graph theory that studies the relationship between these eigenvalues, eigenvectors, and graph properties. A very nice example is the following. If my graph has k connected components, then the Laplacian has k eigenvalues equal to 0. Moreover, the corresponding eigenvectors will reveal the connected component. Basically, the entries of the eigenvector with non-zero values correspond to the nodes of that connected component. It's a very nice result in spectral graph theory. So the idea is to use the spectral decomposition of the Laplacian for network clustering, which is our goal here. So that gives rise to spectral network clustering, and the first step is to connect the cut size with the Laplacian. So let's consider k equals to 2. And for the assignment, the cluster assignment vector, we're going to use the following notation. Minus 1 indicates that the node is in cluster 1, and 1 indicates that the node is in cluster 2. And the reason for using minus 1 and 1, it's because we're going to use linear algebra to compute the cut size. So given an assignment vector z with minus 1 and 1, the cut size induced by this assignment vector is just a z transpose Laplacian matrix times z. The optimal solution to the mean cut problem then is just given by z hat, the minimum of basically the cut size, z transpose lz, while z now is minus 1 and 1, right? It's one of the two values. So in order to solve this, this is a combinatorial problem, which is hard to solve. In order to solve this efficiently, we can relax z hat. In particular, instead of assuming that z hat is minus 1 and 1 for every entry, we're going to allow zi to belong to the real numbers. So it can be any number in the real line. So if you do that, the exact optimal solution to the relaxed version of this problem is V2, the eigenvector associated with the second smallest eigenvalue of the Laplacian. So note that by knowing this, we can actually solve this very efficiently. Good. So here is a simple algorithm for spectral network clustering with k equals to 2. First, we compute the Laplacian for a given graph G. Then we compute V2 the second eigenvalue of the Laplacian, and then we use the sign of the elements of V2 to determine the cluster of each node. In particular, if V2 of I is less than 0, then I put node I in cluster 1, else I put node I in cluster 2. So here's a concrete example, my little network of 6 nodes. We can compute the Laplacian for this network. You can compute the second eigenvalue, which is there in your screen, and you can compute the second eigenvector. So if we look at the eigenvector, we can collect the negative entries in C1, that's going to be node 1, 4, and 5, and the positive entries in C2, that's nodes 2, 3, and 6, and that's our final clustering. And you can see that in this case, the spectral network clustering did a very good job, actually found the same result as Carnegie and Lin, with a balanced partition here. Good. So what about the cut ratio? So we talked about cut size as being not very effective because it sometimes produces clusters that are small, and we can use the cut ratio for that. So we can connect the Laplacian with the cut ratio induced by a particular partition in the following way. Consider a matrix A, which is an n by k matrix, where age IL is 1 over square root of the size of cluster L. Okay, if I belongs to CL and 0 otherwise. So note that in this matrix, each row only has one entry that is non-zero, every other entry is 0. So the cut ratio induced by a particular cluster assignment is given by the trace operation of the matrix H transpose Laplacian times H. Okay. Oh, that's exactly, you can do the calculation, that will give you the cut ratio. So the minimum cut ratio problem now becomes finding H star that minimizes the trace of HT-LH over all possible cluster assignments and matrices H. Of course, this combinatorial optimization problem is NP hard, and again, we can resort to relaxation to solve this problem efficiently. So relaxation here means that H can have non-zero entries, and we can impose a constraint on H such that H transpose H is IK, where IK is the identity matrix with dimension K. That will control H a little bit. So in that case, the optimal solution H star to this problem, to this relaxed version of the problem, is a matrix whose columns are the first k orthogonal eigenvectors of L. So I'm going to take the eigenvectors of the Laplacian and I'm going to stack them one by the other as shown here in the figure, and the k first eigenvectors of L actually will give the optimal solution to this problem, H star. Great. So now we have H star, but we still need to compute or to determine the cluster of every node. Note that H star does not give me that directly. However, I can take a look at the ith row of H star and consider that as the signature vector for node I in k-dimensional space. So Si, the signature vector for node I, is composed of V1 of I, V2 of I, up to Vk of I. Now, the idea is that nodes that have similar signatures in this k-dimensional space should be placed in the same cluster. So now I have a data clustering problem to solve, and I can do that. I can solve this problem using a k-means algorithm. Okay, so I just cluster the nodes in this k-dimensional space into k clusters. Good. So practical considerations for better results. I can use a normalized Laplacian as opposed to just a Laplacian. This provides more stable results when the degrees have different scales. And I can also use more than k eigenvectors for generating the signatures, including when I want to find k clusters. This often also gives more stable results. Very good. Now let's change topics and talk about network clustering using modularity. So the cut-based metrics that we just saw only consider intercluster edges. It doesn't say anything about the edges inside the cluster. However, intra-cluster edges are also very important. So So modularity is a metric that's been proposed basically to compare the number of edges inside the cluster with the expected number of edges that the cluster should have in a random model. So modularity only cares about intra-cluster edges and not about edges between clusters. And the idea is that larger modularity indicates that the cluster has more edges inside than a random model would predict. So the number of intra-cluster edges of a community CL is just given by the sum of edges that are among nodes in CL. The expected number of intra-cluster edges in the same community CL is given by the sum of the probability of being an edge between node I and J, given that I and J are in community L. Good. So now I have two numbers, XL and YL, and the modularity is just the sum over all communities of their differences, normalized by M, where M here is the number of edges in the graph. Note that if my community XL, if in a community L, XL is larger than YL, then this is good because I found a community where there are many more edges than what you would expect from the random model. All right. Now, to compute this Pij, the probability of an edge between two nodes, we have to do this for any real network if we want to compute the modularity. So one idea is to use the configuration model, which is a classic model for random networks, to determine this probability, Pij. In this case, in the configuration model, Pij is given by di times dj divided by 2m, where di is the degree of node I. So I can take a real network, it has degrees for every node, and I can compute this probability for every pair of nodes. So if I substitute this in the modularity function, what I get is this sum for every community L and a sum for every node pair in a community L, Aij minus di dj over 2m. Properties of the modularity value is always between -0.5 and 1 for any graph and any community assignment. And if my graph is a sample of the configuration model with a particular degree sequence, then the expected value of the modularity of this graph is 0 for any k, which is good because the expected modularity is 0 for the null model, meaning the configuration model. Okay, so that's that for modularity, but how can we compute it? So determining the partition that maximizes modularity for a given network is NP-hard. So we won't be able to obtain the exact value, the exact clustering assignment that maximizes modularity. However, we have algorithms, heuristic algorithms to do that. The first one was proposed by Newman and Girvan, who also proposed the modularity metric in 2004. So here's the algorithm. We start with every node in its own cluster, and for every pair of clusters AB with at least one edge between them, we compute the change in modularity when the two clusters are merged. This is delta M AB. That's the change in the modularity of the entire network when I merge cluster A with cluster B. Note that this can be negative because by merging two communities, we can actually decrease the modularity. Then, after computing this for every pair, I actually merge the two clusters that have the largest delta MAB, and this is the greedy step. And then after merging, I go back to step 2, and I continue doing this until the number of clusters is 1, and then I stop. And I return, the algorithm returns the partition for which M was maximum. Properties of this algorithm: the algorithm induces a hierarchy by merging clusters bottom up. Note that at each iteration, I reduce number of clusters by 1 by merging one cluster into another. The algorithm does not require a priori knowledge for k. It's going to do all k equals to n in the very first step, and it's going to end with k equals to 1, and it's going to return the k for which modularity was maximum. The running time complexity of this algorithm is O(n) times m, which is too slow in practice for very large networks. Despite being polynomial, you cannot run this algorithm if your network has millions of nodes. So for that, we have a second algorithm that is a bit more efficient. It's also greedy and faster, and it was proposed by Blondel and his co-authors in 2008. The algorithm is called the Louvain algorithm because that's where the co-authors of this paper were from, the University of Louvain in Belgium. So how does the algorithm work? Well, let's see. We start with every node in its own cluster, just like in the previous algorithm. And for every cluster A, we're going to compute the change in modularity when merging this cluster with a neighboring cluster B. So that's delta MAB, which again can be negative if merging this cluster with its neighboring cluster reduces modularity. Now, here's the crucial step that is different. What we're going to do in step 3 is for every cluster A, I'm going to merge A with the neighboring cluster B that has the largest delta MAB. And I do that only if it's positive. If it's negative, I don't merge A with anybody. And then, using these new clusters, I go back to step 1 until there are no more changes in the cluster assignment, and then I return the last partition, the partition that we found when the algorithm stopped. So the key difference here with the prior approach is that we are merging multiple clusters in a single iteration of the algorithm. This reduces the number of clusters by a half, at least iteration. So let's take a look at an example. So here's our lithograph that we are using, and note that for every node we compute the delta MAB between the node and its neighbors, and each node identifies the neighbor to merge with, the neighbor that has the largest increase in the modularity. That's what the orange arrows are doing. They're pointing to the node to which I should be clustered with. So note that node 2 has no positive gains, and that's why it has no outgoing edge. Now, once I compute this, in step 3, we're going to form a new graph by merging the clusters according to the edges. So the corresponding nodes of the edges are shown in the picture on the right. So in the picture on the right, I only have 2 new clusters, and each of these clusters has nodes 1, 4, 5 and 2, 3, 6 in each of the 2. And now we have an edge rate, which is 2, which corresponds to the number of edges between the clusters. And in this case, the algorithm would stop here, but otherwise it would continue. So properties of the algorithm, it also induces a hierarchy by merging clusters bottom up. It does not require an a priori value for k, the number of clusters. However, the order in which clusters are merged matters, right? How do you process these orange arrows will influence the result of the algorithm. And the running time complexity here is in the order of m times log n, which is more efficient than before, and you can run this for much larger networks. Good. So modularity, there is an issue because modularity is biased toward large clusters. Small clusters will actually reduce modularity, and this was shown in a particular paper, which means that the condition for clusters in the maximum modularity partition is the following: d of a has to be greater than the square root of 2m, where d of a is the sum of the degrees of nodes in cluster A. In the maximum modularity partition, this is true for every cluster. So this example, this figure illustrates this. Consider a network which is a ring of cliques of size 5. The intuitive partition is to put each clique in a particular cluster, since we have clusters of 5 nodes. However, this leads to a modularity value of 0.867, which is not the maximum. The optimal modularity actually is to put 2 cliques together inside the same cluster as shown in figure B, and this gives modularity value of 0.871, which is larger than A. And in figure C, we have a random assignment of cliques to clusters, also showing that if you randomly assign these cliques, ignoring the ring structure of the cliques, you also get a pretty high modularity value of 0.8. So there are issues with modularity, with this limit of resolution for modularity. So another issue is that algorithms for minimizing modularity or cut size often find good partitions even when there are no clear network clusters. So if you take the Louvain algorithm and run it on a random graph with no clusters, you actually are going to find an assignment of clusters that has a reasonably high modularity value. So what the plot here is showing on the left is the modularity value for graphs generated by the Ernst-Rennie model, the preferential attachment model, and the configuration model with zip distribution. And recall that the configuration model is the null model for modularity. And you can see that in all scenarios, a pretty high modularity value was found. And the plot on the right is showing the number of communities found by the Louvain algorithm. It's a pretty high number of communities. So that's actually a general problem with cut-based approach. It's not just a problem with these algorithms, with the Louvain algorithm or modularity. In particular, if you run a cut-based approach algorithm on any graph, it will find a cluster even in the middle of the randomness. And these clusters, they do not reveal any latent information because the graph is random. There's nothing to be revealed. So results, when you run these algorithms, the results that you see should be interpreted with caution, right? It's not the case that the clusters mean any particular information. Good. So that leads us to a principled approach for community detection. Basically, the use of random models that can generate network clusters and that we can use to infer community assignments or clusters. So now let's assume that network clusters are generated by some random process. We assume that we have a model for how nodes are placed into clusters. That's P of Z. Z is our cluster assignment vector. And we assume we have a model for the network is generated given the assignment vector Z. That's P of A given Z. Now A, my adjacency matrix, is a random network. It's a random matrix, but it's conditioned on the cluster assignment of the nodes. And if we have these two models, we can use the statistical inference to determine the best node assignment. Given A, an adjacency matrix that I observe, and the models PA of Z and PZ, the posterior PZ of A is given by applying Bayes' rule, right? BZ given A is just P of A given Z times PZ divided by P of A. Note that PZ of A is a likelihood function of the assignment Z given the observed matrix A. So what we can do, we can run maximum likelihood estimation for the node assignment vector to find Z star that maximizes the likelihood function. And the likelihood function is just the numerator of this equation because the denominator, P of A, does not depend on Z. So Z star can be computed in this way and revealing to us the optimal assignment. That's very nice, but we have some concerns here. First, determining Z star is often NP hard. It's complicated to solve for Z star. Moreover, if I want to apply this approach, I must have knowledge of P of A of Z and P of Z, the models for generating the network and the model for generating the community, the assignment vector. And if you have some data, what is the right model for your data? The third point is that we must leverage heuristics to search for Z star because solving for Z star exactly is often prohibitive, and the heuristics and algorithms for solving for Z star often depends on the model for P of A given Z and P of Z. So in order to tackle this, we're going to make some simplifying assumptions. First, we're going to assume the number of clusters K is fixed and known a priori. We're going to assume that P of Z is simple. For example, it's proportional to the number of nodes in each cluster. And we're also going to assume that P of A given Z is conditionally independent. That means that the probability of two edges, ij and I prime j pi, given the assignment z, are independent, and this factors out. This will allow us to write the likelihood function in a very simple way. So we still need a model for P of A given z, and the most common model used is the stochastic block model, which will be discussed in the third part of this tutorial. So we can also have a model for the edge presence and also edge weights that will depend on the clusters. For example, the density function FLL prime depends on the cluster pair LL prime. So for each pair of clusters, we're going to have a density function either to determine the edge weight or to determine the presence or absence of an edge. And we're going to assume that these functions are parametric probability functions, density functions or probability functions like the Bernoulli, normal or exponential distribution. And in that case, we only need to find their parameters to specify the function itself. Good. So here's a hard clustering algorithm, an algorithm to do community detection in this framework of statistical inferencing. So we're going to let Li of L to be the likelihood function obtained by placing node I in cluster L and not changing anything else. So I have a cluster assignment vector Z, I take node I and I place it in cluster L, and I compute the likelihood function in this scenario. And note that this function, Li of L, can be computed using the parameters of the parametric distribution for the edges. So here's the algorithm. We start with some initial assignment Z0 of the nodes into clusters, and the number of clusters is set to k, and we set t equals to 1. Using assignment at zt minus 1, we compute the empirical p of z and the empirical parameters for the distributions FL, L prime, given the cluster pairs LL prime. So given the current assignment, I compute the parameters of the parametric distribution. Then, for each node I determine the best community, the best cluster for node I, fix everything else. I set t equals t plus 1, and I go again. And I repeat this until some convergence criteria, maximum number of iterations, or until, for example, there's no more change in the assignment of z. So observations here is that the argmax of Li of L can be computed by simply considering all clusters for node I. Convergence to the maximum number of iterations or reaching a fixed point, as I just mentioned, the performance of this algorithm really depends on the initial assignment Z0, and that raises the question how to determine Z0. A random choice for the initial node to cluster assignment is likely to lead to a poor performance. So we have to do a Z0 that is smarter than random if we want this algorithm to give some good results. Okay, so let's talk about a different way to do a community detection using a principled approach. And the idea here is really to generate samples of the community assignment given the network that I have. So what we would like to do is sample Z given A and use these samples to then compute some statistics about the communities of the nodes. To generate these samples, we're going to construct a Markov chain where the state space is a set of all possible assignments. Of course, this is 2 to the power n. This is a very large state space. We won't enumerate this chain a priori. And then we determine simple transition rules on the chain of the Markov chain. For example, we given an assignment vector z, we can choose a node I at random from the current state and place this node I in cluster L with probability proportional to the number of neighbors of I that are in L. So that will create a transition to the Markov chain. And then we can use Metropolis Hastings to induce this above Markov chain to have a P of Z of A distribution in steady state. So I can control for the distribution of the assignment vector to be what we want in steady state. Note that in order to do this convergence, I need to calculate some weights. for the metropolis Hastings, that depends on the model P of A given Z and P of Z. But that's doable if you know these models. Okay, then we can simulate the Markov chain for many steps, and each step is a sample of Z according to this distribution. So now I can use these samples that I generated to compute the marginal distribution for the clusters of every node. Note that Zi now is a probability vector and no longer a number. Zi of L is a probability that node I belongs to cluster L, because in my samples, node I is gonna appear in different clusters. So Z hat IL is the fraction of times that node I appears in cluster L. Now we can use, for example, the maximum of this vector to determine the cluster for node I. And that maximum value indicates the confidence of this assignment. So it's a very different approach that's using this probability Z given A to generate samples and then provide properties of the communities. Good. So let's take a look at what happens when you run this MCMC network clustering on a small network, the Karate network dataset, which is a famous dataset. So here's what we find. The graph on the left predicts 1 or 2 clusters for this network with high probability, and the examples on the right are assignments that were obtained by the MCMC algorithm for 2 clusters. And you can see that the picture in the center, you have the network divided into 2, and the picture on the right, you have the 2 hubs in a cluster and everybody else in a different cluster. So plausible clustering for these networks. A very nice result is that if you apply this technique of Markov chain Monte Carlo to random graphs, what you find is that the number of communities is very low. So for the Eder-Shureni and preferential attachment is 1, and for the configuration model is also a small number. So it's nice that for random graph where there's no community structure, this technique does not find any communities, at least for the ER and PA model. Good. Now let's talk about clustering networks with node and edge attributes, because real network data is increasingly annotated. We have node with attributes and edges with attributes. And these attributes are often correlated with the latent information that the network clustering is trying to find. So here's an example of a social network with some students' first name, which is also an attribute, and the number of messages they exchanged, let's say, in the previous day. And we're trying to cluster this network, and we would like to reveal some latent information, for example, the nationality of these students. So if you take a look, you might recognize the names. Some of them look Brazilian names, some of them look French names, and it's possible that Brazilians communicate more, exchange more messages than the French. So this will be reflected in the edge weights. So we can use the homophily pattern of communication, we can use the name pattern, and we can use the edge weights to try to infer the 2 clusters in this network. And actually, this is the most recent variation of network clustering, to cluster networks where you have attributes both on the edges and on the nodes. And the tough question here is how to fuse these 2 sources of information. You have structural information coming from the network, and you also have attribute information coming from the nodes, and we like to put these 2 things together into a cohesive network clustering algorithm. So one way to do that is to extend our principled approach using the likelihood function to this scenario. Now, along the matrix A, which encodes the relationship between the nodes, we have the attribute vector X, which encodes the attributes of every node. So let's assume that we have a model for generating A and a model for generating X given the cluster assignment Z, namely P of A commas X given Z. We can compute the a posteriori probability using Bayes' rule as we did before, and the last equality here follows because we're assuming conditional independence between A and X. So both the network edges and the node attributes, they are conditionally independent given the assignment Z. So now we can use the hard clustering algorithm that we showed before into this scenario. The idea is very similar to the previous scenario with no attributes. However, we now must consider both functions, p of a given z and p of x given z, and we also need to have an initial assignment z0 that involves both kinds of information, network and attributes. And it's more challenging than in the previous case because of this. Here's a reference for a recent work on this problem, for example. All right, so let's give, this gives rise to our last approach, which is using learning to cluster nodes in the network. And we're going to talk about graph neural networks, which is a technique that has been developed recently to learn things on graphs. So it's a neural network that can learn properties of graphs using node and edge attributes. So the way this framework, the GNN, works is that node and edge attributes are the input to this neural network, and the output of the neural network is a vector for each node. The dimension of this vector is much smaller than n, the number of nodes of the graph. And we're going to call that vector the representation for the node. Initially, GNNs were used for unsupervised tasks like node classification, edge prediction, but recently the GNN has been adapted to other tasks, including network clustering. And the idea here is to cluster the node representations. I use my neural network to generate a representation for the node, and I take these representations as vectors in Euclidean space, and then I cluster these points in space, very similar to what we did with spectral network clustering. So the challenges for network clustering with GNN is actually designing an objective function for the neural network in the unsupervised scenario. This is more challenging. And then defining effective mechanisms to aggregate edge information and node attributes from the neighbors. And the third is actually scaling up these GNN models to find clusters in very large networks. There's a growing recent literature on this topic, and here in the slides are two recent references on this issue. Good. That's the end of part 2. Thanks for listening. Bye-bye.